Yeah, breaking the resistance a little bit, but I've been with SOPREMA Canada for over 9 years now. I've been pretty involved with wind uplift testing for SOPREMA. Canada is both with Canadian standards and FM, so we're kind of really involved in everything according to wind uplift, especially for SOPREMA Canada. So I'm really proud to be here with you today. So here's an overview of what we're going to go through with that presentation. What I want you to get from that presentation is understanding how wind affects a building, first of all. So you've seen a lot of people talk about wind uplift, but how does it come to be? The loads and the resistance, how everything ties up into one thing. So I hope I'm going to achieve that with that presentation. 40 minutes is kind of short to go through everything. So if you have questions, please bear that in mind, and I'm going to answer them at the end of the presentation. First of all, you've seen pictures of wind-related failures on roofs from many presentations. This one's not going to be different. Where we need to start, especially if we want to understand the resistance of a roof assembly, we need to look at what the spectrum of failures could be. You see here, this is a Canadian landscape. It's a little bit more, no palm trees, stuff like that. This is a mild severity failure. By mild, I'm not saying that the roof is good. This needs to be repaired. But when I'm talking about the severity, it's more about the effect or the damages that could be to human life. So you're going to see that this one roof needs to be repaired, but it's not a really problem. It's not really a problem for the safety of a human. So you see some wrinkles. Note that along the edges, the severity or the damages are higher. We're going to understand later bit why perimeter are more damaged. Again, picture on the left, you see a lot of wind or uplift on the perimeter. This is really bad. Again, not that much severe. The membrane, the roofing system is still on the building, which is really not the case for the opposite. This is a building apartment, again in Canada, but the whole roof assembly flew by. So this is really dangerous because people can walk by, receive the roof, it could die, and you see that it's not only the roofing membranes that can fly off, the cover boards, the insulation, and even the thermal barriers on deck can fly off and injure or kill somebody. Here, those two pictures are single plies. Again, we see some membranes on the side of the building. Could have hurt the driver, could have hurt somebody. You can see that this project is not done yet, and there was a wind event that failed the roof. So you see that the insulation was part of the reason why it blew up. Picture on the right, on the left, sorry. I just want you to remember the adhesive pattern. Bear in mind that my presentation is complementary to Brian said, that everything matters and there's no belt and safety belt on roof assemblies anymore. Each manufacturer tries to push the system to the limit. So if you're not following the recommendation, things like the picture on the right, on the left, could happen. Again, on the right, the landscape is a little bit more like Mexico with the palm trees. I believe this was in Florida, but again, what I want you to look at those pictures is the fastening pattern is not random. Each manufacturer is going to test a roof system. They're going to place the fasteners at the right place. This needs to be followed because if you start changing those fastening pattern, you will probably not get the resistance that you wish for that system. So bear that in mind with those two pictures. Recommendations needs to be followed, and this is what's being tested afterwards. So, the basic principle. You saw this picture, I believe, in every presentation. What I want to do now is explain how it come to be, because looking at all those arrows, it doesn't really mean a thing. Let's think about the building as a plane. So the wing of a plane, how a plane will fly, it's the same principle as the wind uplift that goes on a roof, meaning that the wind needs to go around the building. So the length of the travel of the wind is going to increase, meaning that the speed of the wind needs to increase. And when the speed increases, the pressure drops. So that's where the uplift comes from. The effect of that wind uplift is stronger. You see the longer arrows near the perimeter of the building. This is because this is where a decrease of speed and the increase of speed happens near the edge of the building. So that's why perimeters, corners, has a higher wind uplift pressure than in the field. This is exactly how a plane will fly. So the curvature of a wing plane makes the pressure drop on top of the wing. The plane lifts. Same thing with the roof. Hope it helps seeing that picture with some kind of a explanation. So this is a simplified version of the same building that we saw from the side, but now from the top. We can point three types of zones. We're going to have the field, perimeter, and corner. Why the corners are more impacted by the wind? Well, winds doesn't always go right straight on the face of a building. It can go diagonally or at an angle. So that means that the effect of the wind will compound in the corners. So what I'm trying to say is, if you imagine the wind is blowing to the corner, what you're going to see is the effect of the decrease of wind speed on the corner. So that's why you need to have a stronger system in corners. Hope that makes sense. So we talked about pressures. Now building codes or design specifications, we'll talk about loads. Loads are the targets that needs to be met for a building, meaning that you need to have some kind of an idea what's going to be the pressure on the roof. So I try to not go only with American things. I bring something Canada did do as well. So you're seeing the three bases of designs available in North America. You're going to have ACE 7, the data sheet 1-28 from Global, FM Global, and the National Building Code of Canada. What I want you here to remember is that the gust durations and the interval that are based for the wind gust are totally different from each and every one of them. I always look at the AC 700 years makes me a little bit, puts a smile on my face, because probably we never measured 700 years ago the wind speed on a building, but again, it makes me smile a little bit. So just bear in mind that each and every one of them are different, and it does matter when you're going to try to measure the wind uplift resistance of the assembly. Same building, but FM sees it a little bit different. You've seen this picture, I believe. Same three zones: field, corner, perimeters. Corners are a little bit different by FM, so you're going to see an L shape. I introduced also some dimensions. So you see 0.6H, 0.2H. Those are the sizes of those zones. Those zones are a formula of the height of the building. So it means that the perimeter is going to be 0.6 times or 60% of the height of the building. So that's how you can know how big those zones are. Nothing prevents you of treating the whole roof as a corner, But again, it's much more expensive because the systems in corners and perimeters are way stronger, more adhesive, more fasteners. So bear that in mind. You could go and do only zone 3 everywhere. Nothing prevents you from that. So, types of assemblies. This is a Canadian concept. Brian talked about it with the different types of assemblies. In the Canadian standard, there is 3 types of assemblies, so 3 types of way of dividing them. So you're going to have the Mars assemblies. Mars assemblies is the, let's imagine, TPO mechanically fastened. Those would fall into the Mars category. So only mechanical, the membrane is mechanically attached. On the other side of the spectrum, you're going to have the Rs. Rs are no mechanical fasteners at all. This is, in Canada, it's really popular because let's imagine you're going back on a building, you're trying to do the roof again. So, and there's electrical conduits, plumbing, stuff like that. With an R system, you can go and don't worry about damaging anything under the deck. So this is really interesting. And the other type of assembly you have is PARS, which is a hybrid between the two. Why would you go with a PARS? This is, I would say, really popular also in Canada because if you add the slope insulation and the insulation on a building, we can go and look at 600 millimeters of insulation. So that's quite a high thickness. So imagine having screws that are 600 millimeters and trying to hit the flute of the deck, which is quite hard. So that way you can limit the length of the screws and adding the insulation on top of it. So different challenges depending on the market. But I believe here in Mexico, we are mostly talking about Mars. So what are the standards according to North America? You're gonna have the first one, which is NCFM 4474. You've seen those numbers before, but 4474 is especially for the wind uplift testing. So under that standard, you're gonna have 3 tests. So in order to get a rating, you're gonna go in one of those 3 tests. The first one is the pull test, which is a 600 by 600 millimeter sample size. There is no limit pressure to get a rating with that test. Afterwards, you're gonna have the 5 by 9. Those 2 pictures on the middle one and the right one are taken from FM, so the lab in Rhode Island. So 5 by 9, you can test steel and with deck, but you can only go to 90 PSF. So you cannot have a higher rating when you do a test on a 5 by 9. If you want to go higher than that, you're going to go with the test of 12, with a 12 by 24 test. Those are not, by the way, the 5 by 9 test is the real name of the test under the standard. So it refers to the size of the sample, but bear in mind that the 12 by 24 is to get a higher wind resistance or wind uplift pressure. Also, every time you go up in sizes, the more stringent the test is, because we saw it in a presentation, I think it was yesterday, yes. The deflection of the material. So let's imagine that when you have a bigger sample size and you're doing the test on top of those assemblies, you're bringing deflection, shear strength, peeling, which would not be seen if you're doing a pull test. So bear that in mind, that the bigger the sample sizes, the most likely you're going to get a lower result. So you see the 3 tests, but they are all performed the same way. So FM is called a static test. It means that you're providing a wind gust that is stable or flat. So how it works, if we look at this chart, is that for the test, you start at a pressure that is 0. It's going to go up to 15 psf. So psf is pound per square foot. In kPa, I can do the conversion right away, but you would do 15 psf for a minute. If the system is not witnessing, but it doesn't fail, you go up another 15 psf for another minute, and that goes on and on up until the failure of the roof system. So let's imagine for that the last level was completed for this test. It means that you're gonna have a 90 psf because you've reached the 6 levels of the test, meaning that you're gonna have for that assembly a 90 psf rating. This is the same principle for the pull test, the 5x9 or the 12x24, all done the same way. So you've seen that I was talking about, I've shown in the previous slides different assemblies that could be tested. Here's a quick summary of what assemblies and which tests are going to be done for each of those assemblies. So basically what you're going to do is the 2x2 is going to be for concrete decks. All assemblies done on concrete decks are most likely been tested on a 2x2 at FM. Simple. If you want to have a steel or a wood deck, you're going to go with the 9x5, but you're going to be limited to 90 psf. Somebody would say, why would I go with 5x9? People that have been doing testing at FM knows that it's not cheap, so the lower or the smaller the assembly or the test is, the cheaper it is. So if you don't really want a higher wind uplift result than 90 psf, you're just going to limit yourself to the 5x9. If you want to have a higher wind uplift resistance at FM, you're going to go by the 1224 for steel and wood deck. Again, concrete deck, no limitation. You can go as high as you want. We saw a snapshot of roof nav. Again, this is a snapshot of the roof nav. I put that picture there just to point out that once you know the limitation and where the roof assemblies, you can see in the purple shaded column that you see some ratings. So the wind uplift resistance, you pretty much know what were the size of the sample that was tested. So only looking at this, you can see that some assemblies were tested on the big table and the other ones were on the 5x9. It could be a concrete deck, but sometimes there's a little bit of the difference when you look at the deck in the column. So I just wanted to highlight this for you guys. Now, I'm not going to go into that much details about the CSA standard. CSA standard is a very different way of measuring the wind uplift resistance of roof assemblies. This is a dynamic test. This is much more similar to what you're going to find in Europe. So if you're thinking about European products, they are measured. We measure the resistance much more with a similar approach. When I'm talking about dynamic is compared to FM, which the gust is 60 seconds or a minute long. In the Canadian standard, it's 8 seconds only. But there is much more gust on the roof assembly. So this is, and there are 5 levels. I won't go into that much details about why there is, but I want you to remember that the CSA, the approach is let's imagine you had a ruler when you were going at school and you were just bending it multiple times. At one point, the ruler is going to break, not because you just put much more force into on the ruler, it's just because the ruler was fatigued. So there is a concept of when you're doing a load on something multiple times, at a point it's gonna fail. Because same principle with the CSA standard, where we want to put a lot of wind gust on a roof assembly to see the fatigue on materials. So just a quick, bigger snapshot of the levels. You can see that depending on the methods that's been chosen, that needs to be applied for that standard, level A is around 2 to 5 hours long. Compared to FM, it's around 30 minutes at most. So the magnitude is very different. So here is a video of the equipment that we have in Canada to measure the wind uplift resistance. So you're going to see, just bear in mind the size of a 12 by 24. The equipment you see there is 12 by 24. The other thing that we're able to do, I was talking about the 2 by 2 pull test on concrete. We took a different approach. We are able to test 12 by 24 concrete deck as well. So we can do the whole spectrum of roof assemblies with that type of equipment. So that's pretty much it. You see the same chart on top. It goes up. All right. So just a quick overview of the differences between two standards. One is dynamic. Again, this is because multiple gusts are done. Shorter gusts, but much more. FM is a static, so longer gust, but stable over time. Again, I'm not saying is better. Why I'm saying that is based on, if you remember how the loads can be measured, the loads, depending on the basis of design, are different. So the key here is when you're looking at loads, you need to match it up with the same type of standard. So you need to test, if you're measuring the loads according to FM, you need to test it the same way with the standard of FM. If you're measuring if you're calculating the loads according, let's say, to CSA, you cannot take a FM rating because the two doesn't match based on the gust duration and the interval that was taken. So two different animals. I'm not saying one or the other is better, but you can imagine, being Canadian, which one I like the best. So just an overview of that equipment. It's and how it works, because I think it's really interesting to see how it works. I don't know if you ever played with a vacuum. When you put your hand on top of at the end of the hose, you feel the hose shrinking and the motor trying to compensate. Same principle here, but with a 7-ton chamber on top of it. So you see that yellow grill. This is acting similar to a hand, so you're just blocking the air that is being sucked with a big blower within the orange box at the end. So this flap will create the gust. So if you need to have the 8-second gust, it will do the thing. But if you're doing FM, same principle. So some labs in the US do this with this type of equipment, but if you go at FM, it's going to be blown from the bottom. So basically, this is a reason why you cannot test concrete deck at the FM laboratory, because they are blowing air from the bottom. But with that, you can do the same protocol, but from above. So how does it fail? How does the roof assembly fail? Of course, being Canadian, I needed to talk a little bit about the snow. So a roof fails the same way as the snowball effect. For those who never had the chance to play in snow, sometimes you can do a ball and roll it and it gets bigger and bigger. Same principle as a roof when it fails. It means that as soon as there is a fastener, a ribbon of adhesive that let go, the other ones will follow very shortly because they are the stress induced in those other fasteners or adhesive is going to increase. So it's this, we call it the snowball effect. Another thing to keep in mind is that your roof assembly is going to be as strong as the weakest link. Same thing as Brian said, just at the first presentation today, is you need to think about the whole thing. If you forget screws at some places, you're not going to meet the resistance that was measured in the test. So bear that in mind. If you forget something, you're increasing the snowball effect by a lot. So the whole roof needs to be, think about that. So we're gonna end that presentation with some pictures of when we're doing testing and the mode of failures that we can see. So on the left, we see a R system, so no mechanical fasteners. We see the adhesive ribbons that are gluing down the insulation boards to the vapor barrier. In Canada, it's mandatory to have a vapor barrier on the underside or on the deck, part of the building code. But again, not that in too much detail. What you see on the right is a pull-through. It means that the board went through the plate of the mechanical fastener. So again, think about the snowball effect. As soon as one of those fasteners let go, the other one are really more stressed and they're more likely to go. So usually what we see when a test is happening is one screw pops out, it makes a really, really big noise, and afterwards it sounds like a zip. Pop, 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 pop. Great noise, but it's pretty much how it's always happening, is those type of failures. Here you can see a wood deck, fairly common again in Canada, but again, maybe not here. The adhesive pattern of a asphaltic board on top of that roof assembly. I was mentioning at the beginning of the presentation that keep in mind the adhesive pattern you saw on one of the roof that failed. Here you can see that this was clearly not what's been done in the testing. So this, if a roof was to fail, we should see the same type of patterns, because if you're changing the width, if you're changing the spacing, you're not going to meet the wind uplift resistance for that roof assembly. So bear in mind that if you see a technical data sheet and you see some at FM, you have some fastening pattern and stuff like that, but this needs to be respected, because otherwise you're not going to meet the resistance that was tested in the labs. Because again, manufacturers are not putting safety factors, they're pushing the system to the limit. They want to have the best system, so keep in mind that this is what's being done. So if you see that the width of the adhesive needs to be that amount, or the coverage rate, if you don't hit that, most likely you're going to be on the pictures you saw at the beginning of the presentation. I hope that makes sense. So that's pretty much it for me and for you guys. I don't know if you have any questions.